All right, trying to get some videos done during a long weekend here. And this is the last one of the day, gonna get some practice. Speed graphing e to the x, maybe solving some easy equations. Whatever, I got a marker around the glass here. Can I get it off? All right, so here we have at it. We can get the process down probably to 10-15 seconds, graphing an e to the x function with effort and with critical thinking, with practice. Then you can speed up your calculations and hopefully we can have some repetitive conversations about this very important function. All right, so here's an example. Y equals 20 e to the x plus 7. I think yesterday I made a video where I've got the memorization sheet. And e to the 0.7 is approximately 2, e to the 1.1 is approximately 3. E to the 0 we know is 1, having some semblance of what numbers it takes to produce some numbers that are easy to work with, very essential. And I will mention that e to the negative 0.7 gives us a half approximately a half. Remember what negatives do, they reciprocate. Right, so that's the same thing as 1 over e to the 0.7. That'll get you about a half on a calculator. Okay, this is a little bit bigger. 2 decimal places, 0.69, certainly even closer to 2. I think it's 0.4 after that, but I forget. I use 0.7 now. In banking, they call that the rule of 7. All right, so how do we look at this so that we can standardize it, so that we can do the same thing each and every time and get a quick graph in front of us? Well, the first thing is identifying the asymptote. So y equals 7, dotted line. And then if we can make the exponent, however complicated it is, 0, then we've produced the number 1, which means we produce 20 times 1 plus 7. And then 20 is our first differential in this case. And that number is always going to be our first differential. And our next differential is going to be 3 times that, because if we can make this e to the 1.1, we're really making 3 times 20 plus 7. So the issue is making the exponent equal to values, the first one 0, the second 1.1. And if you do that, you got a very quick graph. Just like that, with practice. All right, now, what would double the 20, right, would be a jump of 40. You can estimate that. I hope you can see that 0.7 seems to be positioned nicely between 0 and 1.1, closer to the 1.1, right, to go up 40 units. And I think if we solve this, 40 plus 7 for 47, we can see where that 0.7 comes from, that approximation, with a quick solution here. Right, you're going to subtract 7. That gets you 40. You're going to divide by 20. That gets us 2. The inverse of e to the x, and I'll write that here, is x equals ln of 2. We talked about that yesterday. The ln of 2 is the natural logarithm of 2. We're going to be graphing the ln function, but not in this video. Yeah, it's a little too much for the brain to handle, perhaps, when you're just being introduced to this exponential growth function. And the ln of 2 on a calculator is approximately 0.7. Hopefully you can see it's positioned nicely between 0 and 1.1. All right, so let's break it down into its component parts. All right, there, that's centered nicely. So we're trying to create e to the 0 gives us 27. And e to the 1.1 triples the 20 plus 7 in this model. So here we have at it. I guess we want x over 40 equals 0. And I guess we want x over 40 equal 1.1. Well, that sure seems like 0 here. So 0 is going to get us 27. Right? I didn't write my asymptote dotted line, right? 7 and 20, 27. And 4 times 1.1, roughly 4.4, gets us a jump of 60 plus 7, gets us 67, and we're done. So what's it take? The shape of an exponential growth, labeling the asymptote, and naming 2 points. That's 4 things that you have to do. And you have to convince me before the middle of May that you have ownership of this by being able to do these quickly and easily. That's what you're gonna get graded on. So now what else can we say? Well, all right, let's actually find out the X value that takes me 40 units up to 47. Let's look at that. And let's estimate it first. 0, 4, I think it's about 2/3 of the way there. 2/3 of the way there. So what do you think? Your guess is as good as mine. I'm gonna say 3. I'm gonna say we're around 3. Let's find it. And let's use our rules of logarithms. Hopefully, this is a problem where we can do that without a calculator. Let's see if we can find a y value of 47. Well, I guess we're taking 7 away. I guess we're dividing by 20. And I guess we've got e to the x over 4. I think we have to ln of 2 that to get to x. Where was it? Oh, to get to x over 4. So it looks like it's 4 times the ln of 2. And that's actually the same thing as the ln of 16. You don't know that yet. But let's see if we can find the ln of 16. ln of 16, what's that even ask? What's the ln of 16 even ask? Because you need to answer that question. And you may need repetitive conversations before you can. It's asking, what do you put on top of e to get 16? Well, I know what 16 is. It's 2 to the 4. And 2, I know what 2 is. It's e to the 0.7 raised to the 4th power. I think I can see that exponent now. And yes, it was near 3. 2.8 is a heck of a better answer. So let's see what 2.8 does. I suppose I could have looked at that here and got a quick answer, but I wanted you to think about that up here. So 2.8 divided by 4, 0.7. What do we see? E to the 0.7 is approximately 2 times 20, 40 plus 7. Seems to fit. All right, so I'm showing less and less as we go along because I want you putting in more and more. I have put an asymptote and 2 points, and I've standardized my jumps. What do you think the first jump is? God, I hope to say 12. So we got something that's going to get us 20. What do you think the next jump's going to be? Geez, I hope you say 36. 36 plus 8 seems to be 54. Of course, you got to find the x values that work. And what are the x values that work? Whatever makes this 0. It's going to get 8 plus 12 times 1. I think the number 5 makes that. And what makes this thing 1.1? I think you have to multiply it by 6 and add 5. But I'll show you that over here. Yep, got to multiply it by 6. And I got to add 5. So roughly 11.6. That's an approximation. Gets me 44. 11.6. This is 5. That's 11.6, which is 6.6 units. I'll divide that by 3. 2.2 times 2, 4.4. I think doubling is going to happen around 9.4-ish. But my last guess was too big, and I wouldn't be surprised if this one was too. Because I know that in order to double this, I need that exponent to equal 0.7. Well, 6 times 0.7 is 4.2. And if I add 5, I get 9.2. So that was not a bad educated guess. I thought it was a little too big based on my previous problem. So I would have lowered it a little bit. But 9.2 gets me a jump of doubling 12, should get me 24 units of change on top of 8, which gets me 32. I don't even remember what I asked, but let's see if we can solve this for 32. Well, first thing I got to do is subtract 8. Oh, that's 24. Then I got to divide by 12. Well, that's good. There's a doubling. And therefore, I've got to do e to the, what's the inverse of e to the ln of, so I'm just gonna do that, put that in your head. That's 0.7 roughly, so we gotta change to an approximation. That's 0.7. If I multiply 0.7 by 6, I get 4.2, and if I add 5, brings me back to 9.2. Of course, not every e to the x is growth, because e to the minus x is decay. Hopefully we can see why. You know, e is approximately 2.71 to the x. We call that growth. We've been working with first three problems, but e to the minus x is a reciprocation. And that base is less than 1, which means we are going to start getting graphs like that. But never fear, it's still a 3-to-1 ratio of change. And I got to bring this desk over. I'm gonna get me one of those science cards. There we go. So let's do one where we have a decay, a minus x. And I have a feeling that's going to be 16 units of change, and this one's going to be 48. Well, let's find out. By making minus x over 2 equals 0, I'm shortcutting this now, and minus x over 2 equaling 1.1. Well, this works 0. We know e to the 0 is 1, so 16 plus 7 is 23. This one over here, minus x equals 2.2. Sure looks like x is negative 2.2. Well, that's good because a negative is to the left of 0. And that's going to get me, let's show you, negative 2.2 divided by 2, negative 1.1. That's on your memorization sheet. That's not what I wanted. Oh, there's a minus sign, right? Algebra 1 mistake, minus 2.2. So this is going to be positive, which means that at negative 2.2, that's going to be 3 times bigger. And if that's on top of 7, it's 55. Very rarely do I get through a video without making some stupid mistake. Hopefully you could see all that with the science card. I wouldn't have to worry about it. So we'll do one more decay. And then at least we're up and running, and this video is there. You can look at it as many times as you want until it makes sense to you. So I see negative x. I know I have a decay problem. There's step 1. Step 2, label your asymptote. Step 3, find the x value and y value of that one and the one that's 3 times bigger. So I'm going to set this thing equal to 0. I can immediately see 1903. I got to spend some time here. And I'm going to get an initial jump of 40, which takes me to 42. And then I want this to equal 1.1. So I get something 3 times bigger. So that's 17 times 1.1 is 18.7, I believe. And 18.7, 1903, so 1903 minus x, 18.7, I hope I did this right. So therefore, x is equal to, take 18.7 away from 1903, 1977.3, I think. Hope I didn't make a mistake there. Now you check that out, but it's certainly to the left. Wait a minute, 1877. Yeah, that was another stupid mistake. All right, so if I take 20 years away, that's really odd, isn't it? I got to do 1903, 18.7. I can't believe I have to do this. 13.6, take away 1.187. Oh my God, so that's 81. What did I write there? 6? Oh, my brain is tired. Oh, let's hope that's right. So 1881.6, I hope that's right. I'm not even going to check it. 1881.6. You can check it. If I made a mistake, I made a mistake. But that's going to get me 1.1, which is 3 times 40, 120 plus 2 is 122. Right? And so this one is, hopefully you can see if that's up by 40. This is up by 120. Add 2. Okay, so the process is sound, even if my mind isn't at the moment, which then a lot of people tell me it hasn't been for quite a while. So is what it is. All right, so we got some videos up. We got some new material looking at it. nice point in time in the semester. I was really planning on doing this more towards midterm than it is already. Still a few weeks away, I think. So this will give us added time to practice this, the inverse of these, what those graphs look like, what we can learn from the Ln of X graph by looking at it. And maybe, just maybe, you'll be able to get to calculus and you'll be able to graph these functions, because most of the students getting there now can't. And it's pretty hard to teach the course if you don't have the foundation. So put the effort in, and 2 years from now, you got a shot at pre-cal next term and then calculus. If you want to tackle it, you got to know how to do all this stuff, right? Because we don't have time to teach you the calculus and this in a semester. Pretty hard. It can be done. It's not easy. All right, so good luck with your practice on this topic. See you in class tomorrow.